Binding energy is the energy required to disassemble or break a whole system into separate parts. Nuclear binding energy is the energy that will be required to disassemble or break the nucleus of an atom into component parts. These component parts are neutron and proton, which are collectively called nucleon.
What is mass defect? Mass defect is the difference between the actual atomic mass and the predicted mass calculated by adding the mass of proton and neutron present in the nucleus. The actual atomic mass is less than the predicted mass calculated by adding the mass of nucleon. This additional mass is accounted for by binding energy that is released when a nucleus is formed. When a nucleus is formed, some of the mass is converted to energy, and this result is mass defect. Due to this reason, the actual mass of an atomic nucleus is less than the mass of particle it is made up of. This is the formula of mass defect.
Alpha decay is a type of radioactive decay process in which an atomic nucleus emits an alpha particle. Alpha particle is a helium which consists of 2 protons and 2 neutrons. Uranium-238 has a nucleus with 92 protons and 146 neutrons. The nucleus is relatively unstable due to the large number of protons and neutrons, which result in a high binding energy per nucleon but an overall less stable configuration. The alpha particle is spontaneously formed within the nucleus, consists of 2 protons and 2 neutrons. The alpha particle is ejected from the uranium-238 nucleus. The remaining nucleus is now transformed into a more stable element, which is thorium-234 with 90 protons.
Next, we move on to fission of uranium. Picture 1 shows that a neutron collides with a uranium atom and split it, releasing a large amount of energy in the form of heat and radiation. The analogy works because short-range force between nucleons in a nucleus are similar to the attractive force between water molecules in a water droplet. In particular, force between nucleons and the surface of the nucleus result in a surface tension similar to that of a water droplet. A neutron fired into a uranium nucleus can set the nucleus into vibration. If this vibration is violent enough, the nucleus divides into smaller nuclei and also emits 2 or 3 individual neutrons. Uranium-235 fissions can produce a nuclear generation in a compound consisting of many uranium-235 neutrons in the decay of one uranium-235 nucleus can initiate the fission of additional uranium-235 nucleus such as picture 2. This generation can proceed in a controlled manner as in a nuclear reactor at a power plant or proceed uncontrollably as in an explosion, and the process repeats itself over and over again.
Next, I'm gonna presenting about nuclear forces. For the introduction, nuclear forces, also known as nuclear interactions, are the forces that act between 2 or more nucleons. They bind protons and neutrons together, called nucleons, into the atomic nuclei. The nuclear force is a short-range force and causes the stability of the nucleus. In this article, we will learn about the definition, properties, and examples of nuclear forces. So, what is the nuclear force actually? The nuclear force is one of the 4 fundamental forces of nature. The others being gravitational and electromagnetic forces. In fact, being 10 million times stronger than the chemical binding forces, they are also known as the strong forces. In this section, we will discuss this force in detail. We can define nuclear force as a force that acts between the protons and neutrons of atoms. Second, the nuclear force is the force that binds the protons and neutrons in a nucleus together. This force can exist between protons and protons, neutrons and protons, or neutrons and neutrons. This force is what holds the nucleus together. The charge of protons, which is positive one E, tends to push them away from each other with a strong electric field repulsive force, following Coulomb's law. But nuclear force is strong enough to keep them together and to overcome that resistance at short range. The first property is nuclear force is attractive in nature. It is also acts between similar charges and oppose the Coulomb law's forces. Nuclear forces is similar between protons and neutrons, and it affects both particles in the same way. As a result, it charged neutral. The nuclear force between proton-proton, proton-neutron, and neutron-neutron is the same. Next, the nuclear force has a range of a few femtometers, being very strong at 1 femtometer and insignificant at distance greater than 2.5 femtometers. Nuclear force doesn't have a simple mathematical force unlike gravitational force. Nuclear force also is non-central force, and lastly, it occurs through the exchange of pi mesons. The most obvious example of nuclear force, as discussed earlier, is the binding of protons, which are repulsive in nature because of their positive charge. On a larger scale, this force is responsible for the immense destructive of nuclear weapons. The release of energy when a nuclear weapon is detonated is due to strong nuclear forces. It is also used in nuclear power plants to generate heat for the purpose of generating energy, such as electricity. A weaker nuclear force can transform a neutron into a proton and a proton into a neutron. This force occurs in many reactions such as radioactive decay, burning of the sun, radiocarbon dating, and the others.